the universe shouldn't exist, some of the world's top scientists claim. Experts say, according to the standard model of physics, the cosmos should have destroyed itself when it formed. This is because the universe was born with equal amounts of matter and antimatter, which must have collided and instantly annihilated one another. But this didn't happen, and scientists are still baffled as to why. Researchers have spent years looking for any difference between antimatter and matter that explains why they didn't cancel one another out when the cosmos was created. The latest possibility being probed by researchers was that matter and antimatter may have different magnetism, but new research shows that they are identical, deepening the mystery of why the universe still exists. Antimatter is the mirror of ordinary matter. Normal atoms are made up of positively charged nuclei orbited by negatively charged electrons. However, their antimatter counterparts are the other way round. They have negative nuclei and positively charged electrons, known as positrons. When matter and antimatter meet, they instantly annihilate each other, releasing a burst of detectable energy. The Big Bang is thought to have produced equal amounts of matter and antimatter, and it should have destroyed all matter. But paradoxically today, the universe is made up mostly of ordinary matter with almost no antimatter to be found. Over the years, a range of possibilities have been looked to explain the mystery. These include looking at differences in charge and mass between antimatter and matter. Now a new super precise measurement from scientists at CERN has explored whether the magnetism of matter and antimatter is different. The test shows that they have identical magnetic properties, leading some scientists to question why the universe is still around. All of our observations find a complete symmetry between matter and antimatter, which is why the universe should not actually exist, said Dr. Christian Smara, lead author of the new study. An asymmetry must exist here somewhere, but we simply do not understand where the difference is. What is the source of the symmetry break? The CERN team, based in Geneva, took the most precise measurement ever of the magnetic moment of an antiproton, a number that measures how the particle reacts to a magnetic force. They found that the magnetic moment of antiprotons is the same as that of a proton, but with the opposite sign. While previous research has shown that the electrical charge, mass and other properties of matter and antimatter precisely cancel one another out, this is the first time scientists have shown this is also true of their magnetic moments. The researchers spent 10 years developing a technique to measure this property in both protons and antiprotons. They first established a way to measure the magnetic moment of protons by trapping them in a magnetic field. They then triggered quantum jumps in each particle's spin using a separate magnetic field. A groundbreaking technique first achieved in 2014, but taking this same measurement in antiprotons was made more difficult by the particle's notorious instability. Antimatter is notoriously unstable, instantly obliterating the moment it touches normal matter. This means it is impossible to hold it inside a physical container, so the CERN researchers captured antiprotons in pinning traps. These containers, which are around the size of a Pringles can, store the particles in specialized magnetic and electrical fields. Using an innovative new technique that involves swapping the antiprotons between two pinning traps, the team made the world's most effective antimatter container. Their storage technique allowed them to measure the magnetic moment of antiprotons more accurately than ever before. The result gave a value for the antiproton magnetic moment that was precisely the same, other than a minus sign, as the proton magnetic moment measured 3 years ago. This result is the culmination of many years of continuous research and development, and the successful completion of one of the most difficult measurements ever performed in a pinning trap instrument, said Stefan Ulmer, a spokesman for the research group. Other experts are now looking at different properties to explain why the universe still exists. These include the possibility that antimatter has upside down gravity, meaning it would in effect fall upwards.